Is the ASUS Ascent GX10 the kind of machine that actually makes sense for your AI experiments, or is it just a glorified hype box that will sit idle in your garage? Who should seriously consider dropping that kind of cash on a personal AI supercomputer, and who would be better off sticking with a cloud-based notebook or a more modest workstation? And, most importantly, does the price make any rational sense for someone who isn't building billion-parameter models every night? Link is in the description if you want to check the product details on Amazon. When I first heard about a personal AI supercomputer, my reaction was a mix of excitement and skepticism. On one hand, having a machine that can run large language models locally sounds like a dream for privacy-concerned developers and for teams that need to iterate fast without waiting on cloud quotas. On the other hand, the headline specs NVIDIA's new Grace Blackwell chip, 128GB of unified memory, a 2TB NVMe drive feel like a checklist that could easily be overkill for everyday data science tasks. The biggest hesitation most buyers feel is the risk of buying a piece of hardware that sits half-filled because the software ecosystem can't keep up, or because the cost outweighs the actual productivity gains. Let's break that down by looking at the real-world workflow of a typical AI practitioner. Imagine you're a researcher who spends most of your day fine-tuning transformer models on a dataset that's a few hundred gigabytes. Right now, you probably spin up an EC2 instance, wait for the GPU to allocate, and then pay per hour. With the Ascent GX10, that entire cycle collapses to a few minutes. You power on, the DGX OS boots directly into a ReadyTOS environment, and you can start training on your local SSD. For that specific use case, the speed of having a local 10 GBE network connection and Wi-Fi 7 for fast data transfers can shave hours off your iteration loop. That's a concrete productivity boost, especially if you're working on time-sensitive research papers or product prototypes. Now, who should actually buy it? First, you need to be someone who runs models that genuinely demand that amount of memory. The 128GB unified memory isn't just a vanity number, it lets you keep a whole model plus its activation maps in memory without resorting to gradient checkpointing tricks. If you're working on multimodal systems, large retrieval-augmented generation pipelines, or training models that exceed 10B parameters, that capacity becomes a practical necessity. Second, you should be a developer who values data privacy enough to keep proprietary datasets on premises. Think medical imaging, financial records, or any eye-sensitive training data. The local storage and the fact that the whole stack runs behind your firewall eliminate the legal and security headaches of moving that data to the cloud. On the flip side, if your day-to-day involves fitting models that comfortably sit under 1B parameters, or if you mainly do inference on pre-trained models, the GX10 starts to feel like buying a race car to commute to the grocery store. A mid-range workstation with a single RTX 4090 and 32GB of RAM can handle most of those workloads at a fraction of the price. Also, freelancers who charge per project and need to keep overhead low will find the capital expense hard to justify, especially when cloud providers now offer spot instances that can be cheaper than the depreciation of a $20+ machine over a year. Let's talk practical strengths. The most obvious win is the integration of the Grace Blackwell chip. It's not just another GPU, it's a plug-poo hybrid designed for massive data throughput. In real-world tests that I've seen from early adopters, the chip's NVLink-style memory bandwidth means that loading a 500GB dataset into memory takes seconds, not minutes. That directly translates to less idle time waiting for the data pipeline. The 2TB NVMe SSD, while not the largest possible, is fast enough to keep up with the chip's throughput, so you won't hit a bottleneck when streaming large token caches during generation. The built-in 10 GBE port also makes it trivial to hook the box into a local network of other workstations or storage arrays, which is a huge plus for labs that want to share model checkpoints without resorting to external drives. On the downside, the machine is undeniably heavy on the power bill. The Grace chip, paired with the high-end networking and memory, pulls close to 500W under load, which means you need a robust PSU and a decent cooling solution, something you have to factor into your office's electricity budget. Another hidden trade-off is the software learning curve. DGX OS is powerful but assumes you're comfortable with containerized environments and NVIDIA's suite of tools. If you're coming from a pure PyTorch or TensorFlow background without prior exposure to NGC containers, there's a non-trivial onboarding period. Finally, the price point well into the six-figure range for many configurations means you're committing a sizable chunk of capital. That's a gamble if you're not certain you'll fill the machine's capacity day in and day out. A practical example: I spoke with a small biotech startup that needed to run large protein folding simulations on proprietary sequences. They tried a